Thank you so much for having me, and thanks so much for joining the session. A little bit about myself before we get started. I've been at Uber for almost 5 years now, and I founded there a couple of the data science platforms, including forecasting, anomaly detection, and most recently, with our engineering counterparts, also our conversational AI platforms. Before joining Uber, I was a postdoc at Caltech, where I was working on approximate quantum dynamics methodologies in order to study large complex systems, such as, for example, enzymes. Let me start with what I believe is extremely important to Uber, which is data science. And the reason I'm saying this is for three major aspects. Firstly, we are working in the real world, so we're making real world decisions. Secondly, we're doing this at a global scale. And then thirdly, of course, we want to incorporate local aspects of various different markets as well as user preferences. And in order to do this efficiently and effectively, I believe data science is very much the key to this. Now, at Uber, we have heavily invested in this space. For this reason, we now have over 400 data scientists and more than 500 analysts. Now, given the importance of data science to Uber and the large number of people who are working in this space, we are continuously to actively seek to increase the innovation cycle and speed of the data scientists and analysts. And to this purpose, we have first built a whole wealth of data science tools that can help accelerate this innovation cycle. But we didn't stop there. And today I want to talk a little bit about how we can accomplish faster and more accurate results. In particular, we form teams of specialist data scientists. These are people who specialize in, for example, forecasting, anomaly detection, conversational AI, computer vision, and together with their cross-functional counterparts, build platforms and tools that others within the company can leverage, and really bring these cutting-edge solutions to anyone, irrespective of whether they're a data scientist or not. So to start off with, let's look at the four major stages of a data science project lifecycle that we want to accelerate with various different tools and platforms. We start off with the data exploration phase, which is followed by an iterative development cycle. Once one has found a model that is of sufficient, for example, precision or recall, one goes then to the productionization phase, which is typically done in collaboration with engineers. And then during rollout and post-rollout, of course, there would be some monitoring in place, whether it's A/B tests or switchback tests or anomaly detection down the road. And this really then informs and closes the loop to the next generation of models that are being built. So let's look at some of the tools that our data team has built for each of these stages of the development cycle. For example, we have Kepler.gl. This actually was open sourced a while ago. It has more than 75,000 external to Uber users and almost 5,000 GitHub stars now. It's a web-based spatiotemporal visualization tool that allows for fast, rapid insights generation, even for extremely large data sets. On the development front, we have built a data science workbench that is used heavily throughout data science, analytics, and operations by hundreds of internal users. This is basically an IPython notebook ++ that is deeply integrated into our data stack. It has version control and share capabilities, and most recently was also deeply integrated into our machine learning platform, Michelangelo, to allow for easy productionization of data science projects. I would also like to highlight Horvath, which is Uber's open source distributed deep learning framework based on TensorFlow, which at the time broke new ground in terms of training speed, especially for large deep learning models. And finally, our experimentation platform that we use during rollout. Now, as I mentioned, whilst we're, of course, empowered by all of these tools to move faster as data scientists and analysts, we didn't want to stop there. We really wanted to transform anyone at the company into a data scientist. And our vision here is to provide data science expertise at the touch of a button. And this is really where the teams that are in my organization come into play. These are deep data science experts in a particular field, such as forecasting, forecasting, anomaly detection, conversational AI, and computer vision, so-called data science ninjas, as I like to call them, and in collaboration with their cross-functional counterparts in engineering, product, and design, build internal tools and platforms that others can leverage, where we bring the cutting expertise to anyone within the company, ideally at the push of a button. So we have been working on some of these platforms for a couple of years now, and here are just some examples. On the very left, forecasting and anomaly detection at scale. We also have an experimentation platform. Most recently, we also have been starting to build a conversational AI platform and a business analytics platform. For business analytics, our hypothesis is that we're always going to be limited by the number of humans and human hours to investigate any insights generation. And so we're looking here to leverage algorithms that can at scale scan across the wealth of data that we have to surface interesting nuggets of information that then business analysts, product managers, or operations teams can further investigate in. Today, I'll be focusing the majority of my talk on the forecasting platform as an example of how we were able to accomplish at-scale platformization at ease. The grand vision of the forecasting platform is to provide forecasts at the push of a button. So absolutely no forecasting expertise required. The only input that is needed is from the user is historical data, whether it's in the form of a CSV file or a link to a query, as well as the forecast horizon, as in how far you actually want to forecast. Everything else is done completely underneath the hood on this front. And so here's just an example of the UI that we built for this purpose. We obviously have also an API for programmatic access. And we generate these forecasts that are shown here on the right-hand side in blue, of course with prediction intervals that indicate level of uncertainty in yellow and red to make actionable business decisions. So let's look a little bit at why we would be building such a forecasting platform. We look at three aspects here when we consider platformization. The first aspect is this area of data science going to greatly enhance our user experiences? The second aspect is, do we have multiple different use cases across the company? And the third one is the reusability aspect. How reusable are the various different methodologies or modules that we're building from use case to use case? Since we saw a lot of advantages here in the forecasting space, we decided to do platformization in this data science area. Now, speaking about use cases, I want to highlight three of the very many forecasting use cases across Uber. On the very left-hand side, you can see the marketplace forecasting. Obviously, we want to provide great user experiences, and in order to do so, we want to accurately forecast supply and demand-related metrics at a spatiotemporal, fine granular fashion. But there are many other use cases beyond this. In the middle, you can see our real-time system outage detection use case. At Uber, we have hundreds of millions of signals, whether this is back-end systems that we're tracking or potentially marketplace health indicators. We really want to study here whether the app is not functioning as it should be, whether people cannot sign in, sign up, or take a trip as expected. As you can imagine, with this large number of metrics and the fact that many of these are supply and demand driven, as you can see from this picture here, setting up these thresholds by humans and then also keeping them up to date over time is simply impossible. So we leveraged our forecasting expertise here and platform to build a completely automated tool. Again, people just have to bring us a list of business metrics they want to track or backend metrics, and then we automatically and dynamically set these thresholds for them and also keep them updated. On the very right-hand side, you can see hardware capacity planning. We still have a lot of our hardware on-prem, and so it's important for us well in advance to know how much hardware to purchase and to provision. Particularly tricky is the fact that we have some very high demand days, such as New Year's Eve or Halloween. We're a fairly young company. These are very much week of the day dependent often. And so again, our forecasting platform and expertise can be leveraged on this front in order to ensure that we're not over-provisioning, which would be fiscally irresponsible, but also not under-provisioning, which could cause an outage and erode the trust of our rider and driver partners. So really a Goldilocks principle here, not too much and not too little hardware. So let's look underneath the hood of what the various different life cycle stages are of a forecasting project. In the first stage, there is data exploration and pre-processing. Now, pre-processing is often an overlooked aspect of forecasting and it can be extremely important, often as important or even more important than choosing the right model or model architecture, in particular for machine learning and deep learning approaches. So to this end, we automated the pre-processing step by building a module that both handles and identifies the common pre-processing aspects of any time series problem. The next step is to choose a forecasting method to use. And this can range from classical statistical approaches, such as the well-known ARIMA, autoregressive integrated moving average approach, the Holt-Winters. I included here also the theta method. This is typically a less well-known method, but has a couple of advantages. It is computationally very fast, as it has won an international forecasting competition, M3, and we also have found it to work quite well on our Uber time series. In more recent years, also machine learning has entered the forecaster's toolkit, and you can see some examples here on the right-hand side. We have had particular success with quantile regression forest, which is a cousin of the well-known random forest, and have also studied deep learning methodologies. Now, in a nutshell, however, it is impossible to say in advance which of all of these methods would work best for a given problem. And so this leads me to the next step, which is backtesting. This is really the step where one compares a variety of different models to one another and identifies which model or which combination of models works best. And when considering backtesting for forecasting, one has to keep in mind the chronological order of the data. So one cannot just take out a snippet of data in the middle and train on before that timestamp and after that timestamp, and then test on that data that you've taken out in the center before training, because that would be cheating. One has to train of a portion of the time series up to a certain timestamp and then start testing on subsequent data that follows. And with that in mind, there are two major backtesting approaches. On the left-hand side, the sliding window approach, and on the right-hand side, the expanding window approach. And the names really say it all. For the sliding window approach, you take a constant set of training data that you move along across the passes, dropping more historical data as you go along, as shown in light gray. And then you test on the orange data that is also constant in size. Now, for the expanding window approach, which is particularly useful if one has very little data to work with, one actually increases the amount of training data for each pass, whilst obviously keeping the test data set constant. Now, again, keeping automation and at-scale platformization in mind, we built a parallel language extensible backtesting framework that automatically scans through a whole suite of different forecasting approaches. We've integrated off-the-shelf approaches, but also built quite a variety of in-house proprietary methodologies as well. And that really allows us to quickly surface to any end user the most appropriate forecast truly at the push of a button. And for those folks who want to look into more details of the analysis, we have heat maps like the ones that I'm showing here for illustrative purposes that you can dig into various different dimensions and understand where refinement could happen. But this is not all. It is not sufficient to only be able to accurately forecast a point forecast. Uncertainty estimations or prediction intervals, as they're known in forecasting, are extremely important. And what is a prediction interval? The prediction interval gives you the probability of the forecast to be within the prediction intervals versus outside of the prediction intervals. So if you have, for example, 80% prediction band, then you would have an 80% probability that your forecast would be within that band versus outside of that band. And the reason for this importance is to make good business decisions. So let me illustrate this to you with a concrete example of hardware capacity planning. You can see the historical time series and then the actualized values afterwards shown in black, the forecast in purple, and the prediction intervals in red and green respectively. Now, between these two pictures, the point forecasts are exactly the same. However, the prediction intervals are much more narrow on the left-hand side than on the right-hand side. So if you wanted to estimate or provision some hardware and want to have an equal likelihood of not exceeding the hardware limit, you would have to provision significantly more hardware in the right-hand side example. We also ensure that we have high quality when it comes to our forecasts. We have both quality assurance of the in-streaming data as well as the forecasting accuracies that we produce. And we're deeply integrated into our data and infrastructure stack to allow for programmatic forecasting at scale. So this wraps up the most fundamental building blocks of a forecasting platform. Next, I want to discuss in more detail some of the more advanced aspects that we have been working on in this space. In particular, special events forecasting. So special events such as holidays, concerts, sporting events, potentially also severe weather events can have a huge impact on our business metric, and it's very important for enhanced user experiences to accurately forecast those. As an example, I'm showing here a week-over-week graph with the current week in blue and the previous week in orange for Chicago. And this is a demand metric. And you can see that every time there's a thunderstorm, as indicated here at the bottom, there are huge demand spikes basically occurring. So how do we incorporate and model special events when it comes to forecasting? The classical traditional statistical approaches don't work very well or cannot incorporate exogenous variables. And to this end, we have investigated and spent quite a bit of time on machine learning approaches, such as the quantile regression approach that I mentioned earlier, as well as recurrent neural networks. As the name suggests, recurrent neural networks are very good at capturing sequences within data. And the way they do it is by having the previous state S sub t minus 1 inputted into the current state S sub t. Now, obviously, recurrent neural network approaches are also not a silver bullet. They typically require quite a bit of training data, although in recent months we have been able to surpass this as well. And then often interpretability can be an issue too. Looking at one example architecture that we've been using in order to do event forecasting is the one that's shown here on the slide. Noteworthy in the context of scalability is this pre-training step that I'm showing here on the bottom, which has an encoder-decoder approach that extracts features from the time series in a black box fashion, and which limits the amount of human interaction required for this particular system. The learned embedding is then concatenated with external features such as weather, concerts, events, and then passed through a prediction network, in this case a multi-layer perceptron, in order to provide the final forecast. In case you're interested in more details, we've also published a paper, and the link is here on the bottom. Now, looking at how this method performs on a couple of example cities, we obviously tested it against a naive approach, which would always be the starting point. In this case, we assume the last day equals the upcoming day. Also, the quantile regression forest, a vanilla LSTM, a deep learning approach, and then our method. And you can see that we're getting significantly better errors for the new approach here. As we talked about previously, prediction intervals are very important, and as you can imagine, are not trivial to accurately get, especially for special days that might be rare in nature. Here we have developed and applied a new cutting-edge methodology for this purpose. First of all, see how well we're predicting against the true values in orange, even for special event days, and then how nicely the gray 95% prediction intervals really envelope around the values. We are also heavily investing in developing new cutting-edge approaches. And one call-out I want to make here is a new hybrid approach that we have been developing. In particular, one of our members is now an international forecasting competition winner, thanks to this approach that he came up with. It is a hybrid approach of Holt Winters and recurrent neural networks. And again, we published a lot of technical details here in our blog post. I want to conclude my talk by talking a little bit about the various different phases of commoditization and the strategies we're employing to set our specialist data scientists up for success. Because building platforms is a multi-quarter, potentially even multi-year effort. And so to this end, we have three major stages in the life cycle. The first one is consultation. We heavily embed the specialist data scientists with various different aspects of the business, and they collaborate hand in hand with the core data science teams in these various different areas. This really allows them to understand the business landscape as well as the pain points that our internal users will be facing for these various different areas. It also allows us to showcase successes along the way and have impact as we're helping to solve business critical problems, as well as bringing back, obviously, important knowledge to designing these platforms moving forward. Of course, we pick and choose these in a very strategic way, that we typically work on augmenting the platform with every use case that we take on, or leverage existing building blocks. The second step is to build workflows or templatizations, basically, of these various different approaches. So basically recipes of how to do, let's say, event forecasting, so that any generalist data scientist could replicate this. And this allows us to scale right off the box without having built a lot of infrastructure at that point in time. And then finally, full autonomy platformization. So this is what I talked about earlier. Our end goal is to provide push-of-a-button solutions, as you've seen in the previous UI for forecasting, for example, where we not only accelerated for data scientists and analysts the life cycle that I've shown at the beginning, but really fully automated it all together. And with this, in case you're interested in learning more details about the methodologies that I talked about, the backtesting framework that I touched on, or if you're interested in learning more about other platforms that we're building, we're very actively publishing both on our Uber Engineering blog post, but also at major conferences. And with this, I would like to thank you very much for your attention.